So for our next topic, we'll be looking at flow meters or rotometers. So basically, a rotometer or flow meter is a device that is used to measure the volumetric flow rate of a fluid based on the height of which this ball rises at its steady state. So because it's at steady state, we know that the net force on this ball has to be equal to 0. So the first thing that we want to do in order to derive an expression for the volumetric flow rate based on the height of the ball is we want to do a force balance on the ball. So if we look at these forces, we know that the ball has to have some weight to it. So we want to figure out what the weight of this ball is. Well, we can do that using the densities. We're given that this is a density rho b, and the fluid has a density of rho f. So by using the densities and the volume of the ball, we can determine what the weight of the ball is. We know that the effective weight will be the density of the ball minus the density of the fluid times the volume of the ball, which we know will be pi d naught squared or cubed rather, over 6. And then of course we have to add g, gravitational constant, to make it an actual weight. So this will be the effective weight of the ball using the densities times the volume times the gravitational constant. And then we know that there also has to be some pressure here. We'll call this 1 before the ball. Point 2 will be this gap between the ball and the wall. And then 3 will be above the ball. So because we're doing the force balance on the ball, then we have to factor in the pressures at 3 and 1. So the difference in pressures basically has to be equal to the weight of the ball, because these are the only forces in play. So in order to do that, we'll first set equal, and then it'll be the difference in the pressures, so P1 minus P3, times the cross-sectional area in which they act on the ball. So as we did in the previous videos, we can treat the pressure force acting on this ball as perpendicular to the largest cross-sectional area perpendicular to the force. So that means it'll be the largest cross-sectional area of the ball, which will be pi d naught squared over 4. So this will be our force balance. And now what we want to do is we want to cross some stuff out. So first we see a pi cancels. We see a d naught squared cancels. That turns into d naught on this side. And we can bring this 4 over here. So that'll give us rho e minus rho f 2 d naught times g over 3 is equal to P1 minus P3. And if you look at this figure here, we can see that this area here, A2, is very, very small compared to the cross-sectional area of the entire column. So because of this, once this flow comes through here and then reaches out, there'll be a sudden expansion, which means we'll have no pressure recovery from P2 to P3. So we can say that P2 will be equal to P3. Let's make that P a little bit bigger. And so what I want to do is plug in P2 here. Since we want to figure out the height of the ball, we want the pressure at that height of the ball. So this will be our final force balance, and what we're going to do next is we're going to take this and plug it into Bernoulli's equation to figure out the velocity of the ball at point 2. So now that we have this relationship for the force balance on the ball, the next step is to do an energy balance at point 2. So in order to do that, we'll need to use Bernoulli's equation. So I'll go ahead and write that out. P1 minus P2 over density of the fluid plus V1 squared minus V2 squared over 2 plus G delta Z equals negative frictional heating. So because the change in elevation here is so minimal, we're going to go ahead and say that term is approximately 0. And we're also going to go ahead and say frictional heating in this scenario is also 0. So all that leaves us with is pressure terms and the kinetic energy terms. So now what we want to do is sub in either V1 or V2 for the other one using the volumetric flow rate. So we know that the volumetric flow rate is equal to V1 times A1, which is equal to V2 times A2. So let's just go ahead and solve for V1. So V1 will equal V2 A2 over A1. Now what we want to do is sub this back in here so we can just get one velocity term. So that leaves us with P1 minus P2 over the density of the fluid plus V2 squared A2 squared over 2 A1 minus V2 squared equals 0. So now we want to factor out a V2 squared. So now we get P1 minus P2 over the density of the fluid plus V2 squared over 2 times 1 minus A2 squared over A1 squared equals 0. So now that we have this, we can look at the areas. So A2 here is going to be so much smaller than A1 here, and they're both squared. So because A2 is on top, this term is going to be approximately 0 because A2 is so small. So now all that we're left with is V2 squared over 2 and rho 1 minus rho 2 over the density of the fluid, or P1 minus P2 over the density of the fluid. So now what we want to do is solve for V2. So that gives us V2 is equal to 2 times P1 minus P2 over the density of the fluid, and then take the square root of that. So now you can see here we have P1 minus P2, and we have the exact same thing up here in our force balance. So what we want to do is sub in this in here for P1 minus P2. I'm going to go ahead and erase this to give us some more room. And that will be P2 equals the square root of 2 times rho B minus rho F 2 DOG all over 3 rho F. So we can combine a couple things here. Give us V2 equals the square root of 4 rho B minus rho F D naught times G all over 3 times the density of the fluid. So this will be the velocity at point 2, and we can use this in conjunction with the height of the fluid in order to make the final expression. So before we move on, I just want to take a minute to talk a little bit more about flow meters. So in reality, the walls of this flow meter are not straight up and down. They have a little bit of a slope to them. Now, obviously, I've exaggerated it a little bit here, but that's just to make a point. So basically, the top of this will still have a maximum diameter of d, but we know that the bottom of this will not have the same diameter because of the slope. So what we want to do is use this slope in order to function diameter with the height. So in order to do that, we're going to create an equation of this line. So this ball, it can't fall out of the bottom of the flow meter. So we're going to assume that the bottom of the flow meter has a diameter d naught, equal to the diameter of the ball. So d naught is going to be our starting point. So let's start our equation. And we're going to use the most basic equation of a line that there is. So d is what we want, is going to be equal to d naught, that's as small as the diameter gets, plus the slope of this line times the height. And so the slope of this line we'll just call n. So that will be our equation, and that's as simple as it is to relate the diameter to the height of the fluid, or to the height of the ball, rather. So next I wanted to talk a little bit about A2. So this is a top view of the flow meter, and as you can see, this is the inner circle is the ball with the diameter d naught, and the outer circle is the edges or the walls of the flow meter that has a maximum diameter of d. So A2 is going to be this this strip all the way around the area of the circle minus the area of the inner circle. So let's go ahead and give that a function. A2 is going to be equal, area of the circle is pi d squared over 4 minus pi d naught squared over 4. So it's just going to be the difference in these areas here, and also factor out pi over 4. Pi over 4 times d minus d naught, and those are both squared. So now that we've figured out these three relationships, we need to use an equation that will utilize all of these in order to relate the flow rate to the diameter and eventually to the height of the ball. So the easiest way to do that is to use the equation for flow rate. Q equals V2 A2. So first, I'm just going to plug in A2, which is V2 pi over 4 times d minus d naught, and those are both squared. And then we're going to plug in our equation of a line here that relates the diameter to the diameter of the ball and the height of the fluid. That gives me Q equals V2 pi over 4 times, I'm going to go ahead and FOIL it out because we're going to square this function. So it's going to be d naught squared plus 2 in h plus n h squared. So that's d naught here. Plus n squared h squared. And then we have our minus d naught squared at the end there. So all we want to do is we're going to cancel those two d naughts. And what we're left with here is just the 2 mh d naught and this m squared h squared. And the slope of this line is going to be so small that by squaring it, it's going to make this term essentially 0. So we can go ahead and cancel that. So that gives us the volumetric flow rate is equal to V2 times pi over 4 times 2 mh d naught. And then this 2 and 4 will cancel. It gives us a 2 on the bottom. And so that will be our volumetric flow rate. And now what we can do is plug in the velocity. So we have Q is equal to V2, or we'll plug it in, is equal to 4 d naught times G times density of the ball minus the density of the fluid, all over 3 times the density of the fluid. And this whole thing will be raised to the 1/2 times pi over 2 in h d naught. So this will be our final expression that relates volumetric flow rate of the fluid to the height of which the ball achieves. And if we want to solve this for height, we can do so very easily by just dividing everything across. So that'll give us the height is equal to 2q over pi m times d naught. And then 4 d naught g density of the ball minus density of the fluid, all over 3 times the density of the fluid to the negative 1/2 power. So this will be our final expression solved for the height.